Welcome back, everybody. So during the break, apart from a coffee, we also investigated the open questions that you asked. So I have a few more answers to the questions that have been asked. The first was about the order of the types, and we found it in the MongoDB documentation. Maybe I can just share my screen so that you see it. So you see nulls, then numbers, then strings, then objects, then arrays, then binary data. That's one of the additional types that Bison has. Object ID, also an additional type. Booleans, date, an additional type. Timestamp, an additional type. Regular expressions, that's also an additional type that can be useful. And then there's min key and max key that are the guardians. So basically the elephant you put in the desert to make sure that you find an elephant in the desert in these mathematics jokes. So this is it. That's the sort. And so now to come back to the concrete example, if you have the numbers and the booleans, that if you say something must be greater or equal to 100, then any boolean will be in the return results because booleans are considered greater than any numbers. Okay, so this is the answer here to this question. Then I go back to my slides and at the same time answer the other questions while I make my way through them. So the other question was, does MongoDB retroactively validate the collection? The answer is no. So it confirmed what I said. It's future oriented, right? So it only applies the schema to future updates. When you insert a new document, when you update a document, then it's going to check for validity. But it's not going to retroactively scan the collection or do anything, at least based on our findings. Also based on our findings, if you do want to check for validity for the past, so for the existing collection, what you have to do is to use find, so this selection, and it turns out that you can pass to find a JSON schema. And the way you do is you use the $JSON schema keyword, $JSON schema, and inside that you put literally a JSON schema. That works. And if you do a find with that, it's going to return all the documents that are valid against that schema. And now, if you use it with a $not, so $not and then $JSON schema, then it's going to return to you all the invalid documents. What you do then is you look at the underscore ID and you use the underscore ID to edit the documents to fix them in such a way that they are valid. So that could be a workflow, right? So it's a combination of using find with the schema and then adding a schema to a collection for the future checks. That's the real life usage. For whom does that make sense? All right. What else do we have? We looked whether or not MongoDB, if the data is valid, is able to store in a physically better format, similar to Parquet, saving a lot of space. Surprisingly, we couldn't find anything. So it does seem, and maybe you can also check and see if you find something, but it does seem that MongoDB is always using Bison, no matter what, even if the data is valid against the schema. We found some blog posts that told you how to optimize your layout to save on storage, but that's not based on the actual existence of a schema. It's based on the length of the fields. So they basically tell you need to shorten the fields in order to save some space. And obviously, if you use a data frame approach, then you don't care about the length of the fields because that would be in the metadata, right? Here's my suggestion. That's a startup idea. Build a better MongoDB that is able to store the data as a data frame format if your data is valid. Or write a letter to MongoDB and get yourself hired as an ETH graduate for improving that, and see if you get an ear from them. That would be my suggestion. I mean, after all, you are the future engineers, so you are going to improve all the things that you see can be improved, right? So these are excellent questions, and that will be up to you to make these improvements. Anything else that we looked at during the break? I think that was pretty much it. Okay, any other questions before I continue? All right, so let me continue. The granularity. of the updates, it's exactly like HBase, where it's per row. If you update on HBase, remember, you lock a row, you cannot have two people writing on the same row. In the document store, it's the same. The granularity is a document. You cannot have two people updating the same document at the same time. But you can have multiple people updating the same collection at the same time. That is possible, right? Just not the same document. All right, so this is an important aspect. It's vibrating. What is it trying to tell me? Be again complaining about battery. All right, so now this is a remark that I did. You noticed, and some of you had questions about how it's an API again. And in an API, you have to make arbitrary choices, like the dollar keywords, the use of the points, the order in the sorting order of the types, what else was there, the use of 1, 0, -1, and so on. For this reason, what you need to add on top to have a complete product is then a query language. And many of the document stores, not all of them, but many of the document stores do have a higher level language on top. The one I'm teaching you is JSONic. It's one of the earliest ones that we started already in 2011 developing. But there's also Uncle, there's GraphQL that you might have heard of, and many other languages. In fact, there's 30 of them now and counting. But again, they all look the same or use more or less the same ideas. So the good news is there's 30 of them. The bad news is there's 30 of them. I mean, hopefully one day it will consolidate, like SQL is undisputed for tables. For graphs, GraphQL, by the way, is not a graph language. It's a tree language, despite the name. But graph querying has been consolidated. It seems that all the vendors have agreed on some standards based on a graph extension of SQL. For the trees, we still haven't consolidated anything. And maybe, I hope one day it will happen. Maybe we'll see that in our lifetimes, that we also consolidate these languages. But right now, you have to live with all of these languages. Okay? But that will take care of next week and the week after that when we go into JSONic as an example of such language that is a higher level than an API. All right, so that's how to use MongoDB. And now I'm going to tell you a little bit about the architecture. You might have guessed that if you have petabytes of data, we are going to partition it, right? And this is exactly what we do in the case of MongoDB. And what happens is that we have some keys that happens to be the same keys that we index on that give you the bounds of the partitions, a little bit like the regions in HBase, if you want. And so every partition is also replicated. So now that should remind you of HDFS, right? In HDFS, we both have these blocks. We partition the data, and every block has replicas. So that's the same thing in MongoDB. We partition and we replicate. Every partition like this is going to be handled by a few machines that we call a replica set, a set of replicas, replica sets. And here the architecture is a bit different from what we've seen before, right? We don't have a single coordinator node and all these worker nodes. In fact, we have, for each replica set, we have a few machines like this, right? So it looks different. For one replica set, we have a primary server, the MongoDB server, and then other MongoDB servers that are considered secondary. They store the same data, replicates thereof, but this one is the one that is the preferred machine to communicate, right? So if you want to read or write, you should go to that machine right here, and then the machine propagates to the others, right? And you have that for every replica set. So it means if you have 3 sharps, for example, then you have the first replica set, the second replica set, the third replica set, right? The number of machines in MongoDB in practice, in a lot of places, you count them in your fingers, right? You don't have 1,000 machines. It's more like you have 3 machines, 5 machines, 10 machines. I think I saw some people trying to push the performance of MongoDB until a few years ago. It was difficult to scale. It could be that it improved. So maybe now people manage to use MongoDB with more machines. But compared to Spark or MapReduce or HDFS, we are not looking at that high a number of machines as high as in HDFS or Spark, at least last time I checked. Okay, so this is how it looks like. It's different again from the centralized architecture that I've shown you in the previous week. Now, what happens when you write something? So first you go to the primary node of the shard that you want to write to. That's one of the replica sets. You connect to the primary node right here. What's going to happen is that that node will store the data, apply the update, and then propagate the update to the other machines, the secondary machines of the same replica set. And then they are going to acknowledge. And once you reach a certain point, a minimum number specified by the user, you consider that it's successful. So you don't wait until all of them are done. Maybe you consider that 3 is enough, and then you return to the user. So maybe that's good enough at 3. And then you continue the replication asynchronously in the background. So after you return to the user with an acknowledgement of success, you still continue to replicate until all machines have a replica, right? So again, 2 steps. First, a synchronous part until the specified number is reached. That is synchronous. The user has to wait. And after that, you return to the user, and then asynchronously, you continue to replicate. Does that make sense? Right? It's not new. We saw it in HDFS. Remember, when you write through the name node, there is a minimum number of replication that is 1 by default, and then you continue replicating all the way to 3 asynchronously in the background. Right? It's the same idea. Okay. Any questions? Okay, no questions. So now we are getting to a super interesting part. In fact, I told you it's not a data lake. So it's not like HDFS or S3 where you just drop your JSON lines files in there and then start querying them. It is a database management system where you explicitly insert documents into collections, and then the storage is handled by the document store directly. There is a huge advantage that comes to that you do not have in data lakes. That is that you can build indices on top of the data that make your queries returned very fast. If you want to look up something in a data lake, maybe I have a few examples in there. Imagine you have let's say that's a JSON lines collection, but that could also be a MongoDB collection stored in Bison. And imagine you have billions of them. What kind of queries do we want to do against this sort of data? Perhaps we are looking for one very specific object. Maybe we know the primary key, and then we use, for example, if this is a list of scientists, then we look for Euler. That is just one object, right? That is called a point query. A point query is a selection that is highly selective, so highly selective that typically you just have one document, one record. So this is a point query. If you have to implement that in a data lake or with Spark, how would you do it? You have this on HDFS as a JSON lines file. You need to use Spark in order to find Euler. Yes. You can still continue explaining. Yeah.
I mean, you just specify that the name is Euler with the filter transformation, I guess.
Exactly. So you use indeed a filter transformation with the predicate. So that would be in Python with Spark, that the name is Euler. Now you have to realize that if you do that, the Spark is going to read through the whole collection. It's going to look at all the data in order to do that. It's going to be in parallel, so it's not going to be as slow as if you did it on a single machine. But nevertheless, you might need 1,000 machines in the cluster that are going to read all the data in parallel. And then one of the machine will say, oh, I found it. And then you get with the collect the results. Do you agree? But it's very slow and it's not very efficient, right? So can we do better than that? In document stores and in general, in any systems that are ETL based, you can do it almost instantly, that kind of things. I'm going to show you why, thanks to an index. Now there's other queries that are not so highly filtering because you're not using a primary key, but for example, if you filter by profession, you will find a lot of mathematicians. So now you have larger results, but perhaps you still want to optimize that as well, right? This is also something you can do with a filter in Spark. And then you have queries that are called range queries. In a range query, you don't look for specific values, but you look for something that is within a range. For example, all the years that are after 1900. You can also have an upper bound, right? It can be between 1900 and 1950, for example, right? So this is called a range query. This is a whole different category of queries. We can also optimize them with indices. But now this is a question, how can we make it super fast? And with super fast, I mean much faster than using Spark and filter. And the answer to how it's done, you probably already saw, whoever saw in a book, at the end of the book, there is an index with an alphabetical list of words pointing to the pages. Whoever saw that? Many of you. This is called an index. This is a real life index for humans. The human person who then looks it up. But in fact, if you understand how that works, you understood how these indices work. The only difference is that here it's the computer that's going to look it up. In a book, it's a human, but the principle is the same. So imagine that this, what you see here is the collection of records. This is the book itself. And you want to specifically query the fruits by color. What you can do is build an index. Here it's an additional structure. This is the collection. This is an additional structure that has all the colors here. And then you have yellow points to the yellow fruits, orange, red, green, these two, and brown, and so on and so on. Now, what happens is that the way that this is organized is similar to this alphabetical list of words at the end of the book. It's organized in a way that you can very efficiently locate one of what you're looking for, right? Think alphabetically sorted, for example. What is the complexity of looking up a word in an alphabetically sorted list? That should be an instant answer from computer scientists. Yes? Exactly, it's a logarithmic lookup. All right, in fact, maybe some of you know that we can even do it in O of 1 in what I'm going to show you. All right, so what I'm going to show you now is how we build these things, how MongoDB is going to build these things so as to accelerate the results. So I have a collection here. Obviously, I'm not going to put a billion objects on my slide, so I only put 6 in order to show you how that works. So the idea is that in order to get O of 1, instant lookup, 2 milliseconds, typically in MongoDB to get a result like that, even from a billion different values. Spark is never going to do that in 2 milliseconds. So imagine that I want to accelerate. So what I'm saying in JavaScript is DB scientist, that's my collection, create index on Century, a hash index. And I'm going to show you what a hash index is. But on Century, it means that what I want to accelerate is people who look for a specific century have very fast answers. MongoDB takes care of it for you. You just need to ask MongoDB to do it, right? So you say create index century hash, and then it's going to create the index structure. But what actually happens when you ask MongoDB to do that is that it's going to take the time to go through the collection. So it's going to take a while, right? If the collection is large, maybe it takes a few hours to do that. And then you can continue to use MongoDB, but it's just going to be slower during a couple of hours. And then what it does is that it goes document by document. It says, okay, now we have century 20. The way that a hash index works is that there is a magic function that we call H, that's called the hash function. It's a magic function that eats anything and it spits out an integer. That's a magic function, comes from cryptography. It has a few desirable properties. One of the properties is that collisions should be rare. It should be very hard to put different things that give you the same integer. That's called the collision. And in cryptography, we also want it to be difficult to invert, meaning that if I give you the integer, it's very difficult to find something that would give you the integer, right? So who already knows these things from cryptography? Many of you, right? So here we use these hash functions, not for cryptography, but for indexing. what are we interested in that function? We are interested in the fact that it's deterministic. It's always going to give you the same integer for the same input. And second, it's very fast. In fact, when you implement a hash function, it's a couple of additions and multiplications and modulos, typically in the way you do them. So very, very fast to do. Imagine you have a string, you want to compute a hash. Imagine a Pac-Man that eats the string using plus multiplication and so on, and then spits out an integer. So that's very efficient. So for 20, if I put 20 in H, imagine that I'm getting 0 very quickly. So 0, I'm going to use position 0. It starts counting at 0 let's say in C. So I put the value 20 in there, where the hash function told me, and then I add a pointer to my document. The second one is also 20. So that's also it's deterministic, so it's still 0. I add a pointer. Then 19, so H tells me 4, right? It's unpredictable, right? It's deterministic, but it's spreading it all over the place. So here it's 4. So I'm putting 0, 1, 2, 3, 4, 19, pointing to the document. Then I have -4, spits out 3 for whatever reasons. Then 3 is there, you point to the document. Then we have -6, gives me 1, put it in there. And then you have 20, that's again here. Here we were lucky, we don't have any collisions. If you want to avoid collisions, you can try to have a very large array, right? The larger the array, the rarer the collisions. In practice, you could have collisions, but then that's okay. It's like you make them roommates, right? If you have two values that land in the same position, you would just add a list structure and you have an extra lookup through the local list, right? So even if there's a collision, that's nothing we can't handle, right? We can deal with collisions as well. But still, the less collisions you have, the better. So you need a large table. But now, how does it work to query this collection? So now I did my create index. MongoDB did that in the background. And now somebody says, okay, now find the scientists in the 19th century. Who sees that that's O of 1? It's instant. And the reason is, doesn't matter if there's a million, a billion, a trillion documents in there. The reason is you take this 19, you put it through H, that's O of 1. H gives you 4, you look it up. Also O of 1 because that's random access memory, right? You can directly look it up where it is. It's very common for the index to be loaded in memory. By the way, it's an ideal case. So typically this is in the memory of the machine, not on the disk. And then you follow the pointer. That's also O of 1. Even if it's on disk, it would tell you where to read from the disk. So you just get the block from the disk where this document is located, then you read it. O of 1. Who sees it now? All right, so this is extremely efficient, instant. But there's a few drawbacks. The first drawback of any index is that when you build the index, that takes time. So the index doesn't appear out of nowhere instantly. It takes a couple of hours to build the index, right? So you need to figure out which indices you built and build them. But there is a problem, is that the H function spreads the numbers all over the place in something that looks a little bit random. It's not true randomness, let's call it pseudo randomness, but it's still a bit random. So you have no guarantee on a range. If you have a few consecutive values, like 1, 2, 3, 4, they will not be together in the hash table. They will be spread all over the place. So who sees that a range query you cannot use a hash index for a range query. If you ask for all the centuries between 15 and 20, there is no easy way. The only thing you can do is look for 15, then 16, then 17, then 18, and so on. So you have to iterate through your range. So hash indices do not help with range queries. Then in real life, hash functions are not perfect. There will be collisions that we need to handle. And then if you want to avoid the collisions, then you need a lot of space, right? So there's a lot of wasted space in memory because of that. This is a general principle in computer science. There is no free lunch. If you want to save time, you need to spend space instead, right? It's faster, but it uses more memory, right? So it's a general rule. So So for this reason, we have other kinds of indices that are called tree indices or B trees, B plus trees. Some of you, I assume, saw that during your bachelor's. Who saw B trees, B plus trees? Many of you, but I know not all of you, but many of you, especially those that studied in Germany, Austria, Switzerland. Here, there's most of the time database lectures on the bachelor's. All right, so trees. So in a tree structure, what we do is that we organize the data in such a way that it is sorted. But let's say here you have possess, right? And everything that is smaller is on the left, everything that is greater is on the right. What's more, we don't have just two like a left and a right, but we also have multiple values on each node, right? So for example, everything that comes before com is on the left, between com and is here, between is and merely is here, and after merely and before possess is here. This is called a B tree or a B plus tree, depending on the exact structure. Why are we doing that? We are doing that because when you read and write to and from a disk, a drive, you do it in blocks. You never read just one bit, right? You read a whole block. That's something I've already explained. So the goal of the design of this tree is here, is that when you have something here that contains the leaves, when you read them from this, you ideally want that to be a full block that matches the size of a block on a disk, right, to optimize. So this is the way you design them. So now, the problem with B trees and B plus trees is that it's not a standard definition. There is not a unique way of doing that. And if you look at plenty of places like textbooks or Wikipedia or implementations, you will see that there is no standard uniform definition in terms of how you build them or parameterize them. The principles are the same, but the conventions can be different. So I'm going to take a few conventions in this to explain them. But basically, the idea is that all the leaves have to be at the same depth. So here it's exactly 1, 2, 3 levels in total. So the depth of 2 here. All the leaves must be at the same depth. And then there is a constraint on the number of children for, except of the leaves. Of course, the leaves have no children, but here, for example, we have 4 children, 1, 2, 3, 4. And we have a constraint, for example, that it's between 3 and 5. So you can have 3 children, 4 children, or 5 children, and then you're good. The only exception is the roots that can have less than that. Who was in information retrieval? Okay. For you, it's easy because you've already seen that, right? It's a déjà vu. So that's great news for you. All right. Now, these two values here, 3 and 5, in fact, it's not 3 and 5, it's D plus 1 and 2D plus 1 for some D, and we choose it in such a way that this corresponds to a disk block, very roughly. And so what happens is that the values of your index, so if you index a specific field in your collection and you look at all the values, they end up on the leaves of the tree. These are, for example, all the possible values that we found for the field we want to index on the leaves. And these values here are only for the lookup. These are like shields that tell you go left or go right, right? This is the only use of this value in here. This one tells you everything on the left comes before possess, everything on the right comes after possess, and so on. So now you have to imagine that to find your way through it, you start at the top, and you ask, okay, should I go left or right, depending on what I'm looking for? And then you go down the tree, you find your way to the leaf. What's the complexity of that? It's logarithmic, exactly, in the number of values in there. It's logarithmic. Okay. One thing to be careful about is that if I tell you it has to be between 3 and 5 children, what does that tell us about the number of values that we put in there? Well, you have to be careful because there's an offset of 1. If you have n trees, do you agree that there are only n-1 intervals between the trees? It's the same for the children. If you have 4 children, do you agree you have only 3 values in between? There's 1 less. That's exactly the same consideration of the tree. So saying that I have between 3 and 5 children is the same as saying that I have between 2 and 4 values, right? That's equivalence. Okay, that's what I'm saying here, right? So you have here 3 children, so that means 2 keys. And here you have 5 children, so that means 4 keys. Now I have an animation for you. It's when MongoDB actually starts building this thing, how it actually looks like. So what I'm going to do is imagine that we are indexing a specific field of a collection. It turns out, but this is totally luck, that it's increasing integers. In practice, that's not going to be that, but it's just to give you an example. Imagine that I have 1, then 2, then 3, and I just keep adding them to my B plus 3. So 1, 2, 3. I just keep adding them, 4. And then at some point, I'm going to break my interval rule, right? I'm not allowed to have more than 4 values. 4 is the maximum. Now I have 5. What do? I split it. Now I get one more level. You see, I have 1, 2, 3 on the left, 4 and 5 on the right. And here I have this 4 that tells me that everything on the left is less than 4. Everything on the right is 4 or more. Then 6, 7, 8. Again, I have too many here. I need to split it. So that basically just, let's split it here. Now you have 4 and 7 at the root. I continue to add like 9, 10. Oh, no, I again break that rule. I split it, no problem, and so on. So now let me fast forward a little bit. So now with just 4 in here, I managed to fit 16 numbers. Then comes 17, so I have to split it. But now I have the problem here that there are too many. Then I split it again, and you see this is how we keep adding layers and layers and layers. And it just grows and grows and grows as you add the values in there. And this is what MongoDB is going to do, right? So what I'm showing you here is called the B plus tree. B plus tree means that the values are all at the leaves. This is what B plus tree. With a B tree, they could also be here. But in a B plus tree, these values here are only for comparison. It's only for finding them. But the values of the collection are actually at the leaves. For whom is that clear? All right. So now let's apply it here to this collection, right? So now I have my 6 documents, sorry. So I'm going to build, for the example, a 2, 3 B plus trees. It means that I want between 2 and 3 children per node, just because I need a small example. So now let me start with 20. There's only one node. 21. 19, that's too much, because between 2 and 3 children means between 1 and 2 values, right? Look at the virtual children here. There would be 1, 2, 3, 4 children virtually. They don't exist, but there would be 4, so that's too much. So I split it like this. Now I'm good again. Right? I have a B plus 3. Then minus 4, that's too much, so I need to split, that's fine. Then minus 6, too much, so I need to split. Here I can just reorganize by just moving over the 19 to the middle, then I again have only 2, and then 20. This is a tree index over century. The former one was a hash index, now it's a tree index. Now it's no longer O of 1, it's logarithmic, right? So it's a bit slower. But what happens is that now, so I can do, of course, a lookup on a specific value, but not only, here I can even do a lookup on an interval. I can even specify like century between this value and that value. For example, those that are greater than or equal to 19, then I just look up 19, I just start at the top and find my way through it, right? So you will very quickly arrive here. Everything greater than or equal to that, that's very easy, you just take that. Then you follow all the pointers, and then you return the documents that correspond to pointers coming from there. Who agrees with that? Very good. So it's logarithmic for the lookup. Of course, you need to be careful because it's logarithmic, but think about what you're doing, right? Imagine that here, your interval is so large that you're returning almost the entire collection. Of course, then it's not logarithmic, but it's not because of the tree. It's because of the size of the results that you would have more than logarithmic. Okay. Who is with me? So we've seen hash indices, instant, but they only work on specific values. You cannot have intervals. Tree indices, B plus trees, they are a bit slower, logarithmic instead of instant, but they work on intervals. Right? Now, what happens with MongoDB? MongoDB is giving you one index out of the box for free. You always have it. This index is based on the only field that always exists, and that's the underscore ID field. Right? This one always exists. So MongoDB will always build a tree index on underscore ID. What does it mean? Is that if you ever want to look up a document with its ID, it's very fast. It's logarithmic. Okay? This is called the primary index because this one always exists. The other indices are called secondary, but this you need to ask for them. It's not going to do it automatically. You need to explicitly use the create index that I showed you on a slide before and request the creation of indices on other fields, right? And they are called secondary. When you start creating an index like that, it gives you a few benefits. The obvious one is performance improvements. When you execute a query and specifically look up the fields that you have indexed, it's going to be faster. A second thing that you can do once you have created a tree index is that you can ask MongoDB to partition the data based on that field that you've just indexed. So the partitioning of the collection is aligned with the indices that you have. So if you don't have any index, the partitioning is going to be done based on the underscore ID. Right? If you create other indices, you can ask MongoDB to partition the data based on that other field. Okay? All right. So now let me give you an intuition of what happens when you use the indices. The idea is that if you don't have any index, then you just have to read all the data, right? So you have to go through all the data. If you have multiple replica sets, then of course you can look at the replica sets in parallel, but still it takes a lot of time. So what happens is that you read it all from the disk, and then you apply the predicate in memory, and then you filter. But this takes some time. If you have an index, then what you are going to do is look up the index. The index is typically in memory. So your index is directly going to tell you, this is where you need to read on the disk. This is what the index gives you. So it's going to tell you, don't bother reading that or that or that. This is not what you're looking for, but the index specifically tells you read this, 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 this. And then you can load into memory only the documents that the index told you to load. In simple cases, you're done. This is exactly the results of your query. If the index is exactly matching the query predicate, in real life, it's not that simple. In real life, the index partially filters the documents, but you still need to apply more filtering in memory. I will show you concrete examples of that. So what is the benefit? You read less from disk. This is the benefit of the index. The index directly tells you this is what you need to read from the disk, and the rest you can just skip. For whom is that clear? Very good. So now concretely, imagine that I create an index on name.last. So again, the dot means that it's nested. So I'm indexing the value associated with last within name. And I'm creating a hash index. So I can only do equality lookups. I cannot do ranges. And now I have a query that turns out to be exactly the same. This is the easy case. This is where the index directly gives you the results. So you don't even need to do extra work. Who sees that? That this is super fast. This is O of 1. Right? Who sees it? All right. Again, because it's the same here in my index and in my query. Now, I have another query that is more complex. It's a conjunction. Remember that if I have several things here, it's an AND. So professional physicist AND theories relativity. Do you see that what MongoDB will do, it will figure out that this part here, it can use the index. So it's going to use the index to specifically read the documents that are physicists. But do you see that this here needs to be done additionally? So after you have used your index to process that part, you additionally need to do some more filtering without an index. Who sees that? Right. So this is what I meant here when I said there's more work required in here. It means that for maybe one of the keys that is indexed, we can use it to read from this just what we did. But then if we also have another key that is not indexed, then we need to do it in memory, and that takes a bit more time. So this is an example where the index gives you a direct result very fast. And this is an example where it's a bit slower than if it had been a direct lookup, but it's still going to be much faster than if you didn't have any index at all. If you didn't have any index at all, it would have taken forever. Okay. Here's another example. We have this time a B+3 index, so a tree index. How do we see it? I'm sorry for the arbitrary decision, but in order to get a tree index, you need ones and minus ones. So hash is for a hash index, ones and minus one is for a tree index. Ones mean ascending, right? So it's by birth ascending and then by death ascending. Now, if I have a tree index on these two keys, you can see it as a compound key, right? It's sorted lexicographically first by birth date and then by death date. And then this is going to take log n, O log n. Who agrees with that? Right? It's a lookup, logarithmic time because I have a tree. But now, just to show you an example of -1. So -1 would just mean that for the same birth, the deaths would be just ordered the other way, right? -1. It's the same 1 and -1 as in the sort function, if you remember. Yeah, I just clicked too much. Not so fast, yes. Now, you know that if I use a tree index, a B+3, which I do with a 1 here, birth ascending, this query is also going to be able to use the index. It's a range query. I'm looking for all the births after 1946. So it's going to only read from disk what is in that part. So here you can skip. It's a bit faster because you don't even bother to read what is before 1946. Okay. So in that case, we are faster with the index than without the index. And in that case, if I only indexed on the birth date and I have two criteria here, it's exactly as before. For this one here, the index accelerates it a little bit. So you would first read from disk like this. And then that part you do in the memory. You cannot use an index for that. For whom is that clear? All right. So what MongoDB does is that whenever you give a query to MongoDB, it first analyzes the query and comes up with plans. Maybe it's going to make 10 different plans that use the index in different ways. Then it's going to calculate the costs of every plan, and then it will select the plan that is the least costly, right? So it really tries all kinds of strategies and then finds out what strategy it thinks is going to be the fastest. And so in that case, we would expect that the strategy would be to use the index for birth and then post-filter with death in memory. Okay. Now it becomes a bit, requires a bit of thinking. Maybe I can finish on that. Imagine I have a compound key in my tree index. The first key is birth, so all ordered by birth, and then for the same birth year, ordered by death year of my scientists. Do you agree that this query can use the index even though it only uses birth? Who sees that? Who sees that this is because it's a range. It's the range of all the birth years combinations between the birth and the earliest possible death date and the same birth and the latest possible death date. It's actually a range. Who sees that this is a range compared to this, right? Okay, so this is the reason why this here actually also is faster with this index. But this wouldn't work if I would only query death alone. That only works if it's the first one. Because if you did it based on death, it's all spread all over the place. If you look at all the possible births, it's spread all over the index. So that only works with the first one. Okay, so I'm going to stop on that. I'm actually almost done with document stores. I don't have so many slides, but I will finish tomorrow. Just before I let you go, still want to check how you are. That basically decides on the length of the FAQ session tomorrow. So tell me Should I accelerate? Should I slow down? All right, very good. So the speed is good. Before you go, just one thing. I heard one of you said great TA to Luca. So congratulations, Luca. If you love your TA, send them an email and tell them that you love them. That's always something that they like. So it encourages them. So thank you very much and see you tomorrow for the continuation.